This next major topic is on stereochemistry, and we have a lot of new key terms. Some of the more important terms we'll have all quarter. The first being chirality here. Chirality is a phenomenon that was observed a very long time ago, back when they were basically dissolving things up in solution and hitting them with any kind of electromagnetic radiation or light that they could think of. So when you put a sample in solvent and expose it to polarized light, they found out that you would get different responses with rotation of that light measured in the positive or negative direction. What was the discovery related to this was that compounds that were otherwise identical in every way, which they thought was simply just one compound, rotated light in both directions, or one or the other, I should say. And so it revealed that that compound was in fact two different compounds. This phenomenon is the result of having a chiral center. That is an atom, usually carbon, that has four different groups attached. So in order to recognize the chiral center, you have to have good knowledge of structure and bonding and understand and recognize that there are four different groups attached to an atom, like carbon. To get from one version to the other, you have to basically detach and switch any two of the four groups. So, as I've said before, anytime you have to detach break bonds, switch them and reattach them, you're dealing with two different compounds. When you do that, you get two versions of a compound that cannot be superimposed. So seeing if they can be superimposed is a test to see if compounds are the same or not. If they can't be superimposed, they're definitely not the same. Here's an example of this. So notice this molecule has four different things attached. This atom, carbon, has four different things attached to it. By switching any two of them, you get the two different versions of the compound that cannot be superimposed. Proven to be different because they can't be superimposed. So we call these as having two different configurations. That's a really important term. Configurations rather than conformations. We also call them enantiomers. And the mers, notice, comes from isomers. So it's a type of isomer called an enantiomer. They're non-superimposable mirror images. And it's interesting that it turns out that they're mirror images of each other. When nature makes molecules, it's through the process of biosynthesis. Nature often biosynthesizes only one enantiomer, or one version of the molecule. Now that we know that there's two molecules rather than one, we need to have different names for them, and we usually use R and S designations, although in biochemistry these will often be referred to as L and D alternatively. We'll focus on R and S. The first job, and the next video will go into how to assign R and S designations. Or configurations, I should say, maybe. The first task, though, is to recognize what and where the chiral centers are. And you absolutely have to use the wedges and the hash marks. Otherwise, a straight line doesn't tell anything. It leaves the configuration completely unknown. So if I see these problems without the wedges and hash marks, I'm just going to say I don't know what molecule I'm looking at. So some simple examples of what is a chiral center and what isn't. Say you have this molecule, and the eye is drawn to where the wedges and hash marks are, and the question is this a chiral carbon? And does it have 4 different groups attached? Well, here's one group, here's a different group, but in these directions, you never encounter a difference, a point of difference. This is a CH2 implied, same here. And if you continue this process on through, you never find a point of difference, and you end up just here, which is the same. And so this is not chiral. And so therefore the molecule is referred to as not chiral. If a molecule has a chiral center, it's referred to as a chiral molecule, or more than one chiral center. In order for this to become chiral, we can just make a difference, for example, here. So now we have one group, a different group. Now what we see here is that we have a CH2 and a CH2, so they're not different, but you can't stop there. You have to keep going until you find a point of difference, or until you don't find a point of difference. So keep going out to see if there is a point of difference. And in the next location, you immediately find a point of difference. Therefore, this carbon here is chiral. We'll designate it with an asterisk. Chiral. Now, because we know it's chiral, we know that it has a non-superimposable mirror image that is an enantiomer of it. It's pretty easy to draw the mirror image. One way is to just switch any 2 groups. Remember, if you just detach and switch any 2, you get the non-superimposable mirror image, as we proved above. So to get the enantiomer, I could just draw this by switching these 2 and not switching the other 2. Of course, if you switch all 4, you're back to the same molecule again. This is the enantiomer. Another way to look at it would be, I could draw the non-superimposable mirror image of this, pretending I have a mirror in between. So the mirror image of that is this. And notice you cannot superimpose these, because if you try to flip this over, the double bond will overlap, but now the bromine and hydrogen will switch places. So I kind of like this visual way of doing it, or just in a simple case like this, switching any 2 works. Just never forget that if you have to keep going out, and it doesn't matter how far out you go. So in a case like this, for example, all right, so we'll do just another simple example like this. So Cl, and then you have some long chain going down, long chain going down. If there's a difference here, that makes this chiral. So, like I said, in the next video, we're going to learn how to name these 2 different versions, for example, of a molecule. Many molecules in nature have multiple chiral centers. So here's penicillin G. We all know what penicillins are. Clearly, this molecule has a number of chiral centers. It's pretty easy to see that you have an implied hydrogen here, and this is a chiral center. That carbon has a nitrogen on it, a carbonyl carbon, a hydrogen, and a carbon with a hydrogen, a sulfur, and a nitrogen on it. So definitely 4 different groups attached there. That is a chiral carbon. This is a chiral carbon. It's got a hydrogen, sulfur, nitrogen, and carbon attached. This is a chiral carbon with a nitrogen, carbon, implied hydrogen, and a different kind of carbon, carbonyl carbon, attached there. So this molecule has 3 chiral centers. Notice that this is not a chiral center because it has 2 groups that are the same. In looking, remember, just you're going, as soon as you find a point of difference, they're different. And if you don't find a point of difference, they're not different. So finally, there's more wide importance of this phenomenon. So in the drug field, it's often true that R or S, or in this case, as it's shown, L and D molecules, will either bind or not bind to proteins like enzymes. So drug action is often due to compounds binding to enzymes or proteins or receptors, but it's often true that those compounds have to be one enantiomer and not the other. This enantiomer binds to the receptor site perfectly. Its enantiomer does not bind to the receptor site and does not work. In fact, it could bind to a different receptor and cause harm. So many drugs are chiral and must be sold as only one enantiomer. Another example is the common big molecules cellulose and starch. Cellulose and starch are virtually the same molecule, but one of them makes up the structure of cell walls in plants and is really rigid. That's cellulose. Starch is like a potato. They're long chains of sugar. Cellulose and starch differ only in one position, having a different configuration. So, and you can see it in this video, like right around there. Well, I don't know if you can see what I'm pointing to, but you can see there's one position switched. Because of this one change, we can digest starch, but we can't digest cellulose. We don't have the right enzyme to digest cellulose. Cows do. So cows can eat grass that has cellulose and digest it. So plant-eating animals can digest cellulose a lot of times. Okay, so in the next video, like I said, we're going to learn how to name the 2 different enantiomers.